This is the Holotron. It is the first system that allows for realistic walking in VR with force feedback and balance feedback. Later versions will use an exoskeleton for the whole body, including hands. Holotrons might well be the only systems that will ever allow for realistic VR and lifelike remote operation of humanoid robots. Effectively, a Holotron is like the holodeck and beaming from Star Trek combined. Everything in this video was done with force feedback and balance feedback, and I am controlling the avatar according to the physics in the virtual environments. So all the motion is completely physics-based. Here you can see how you can step on movable objects. You can feel the blocks tilt and how you slip on them. You can feel the interplay of static and dynamic friction. You can also sit on objects. Here I let the avatar drop on the ledge and then I push myself off. Objects, here the movable ground, can also move you, the user, so the environments can affect the avatar and also you as a whole. Here I'm operating the avatar at 1/20th of Earth gravity. This is coming very naturally from the physics simulation. Doing something like this is important for space applications like spacewalks, or if you want to simulate working on Mars or the Moon. Of course, you will be able to operate humanoid robots in lower gravity or space as well. And here you see the avatar quickly dropping at normal gravity. I tried to do something like an Inception scene with the rotating room where I wanted to walk on the walls and the ceiling. That did not work here due to time constraints, and I was completely buried in a pile of debris that got me locked up. So here I try to enter the wall and get hit by a chair. You'll see how the avatar and the user can be free to rotate in all directions. Here the avatar and me drop quite a bit at 1G while walking down some steps. Here I'm using a skateboard in VR and I control it by shifting my weight by applying forces. You can actually skate in large environments and over stairs. It can be pretty violent. This also works with the virtual reality headset, of course. The first-person perspective is in the center. The system gives a really nice impression of the state of the board and of what you're doing in there. Here I tip over, so accident, crash. And here another crash where I drove into that concrete base. And now I'm going down the stairs again with the VR headset. You can see how all the details of the stairs are displayed to you in real time, just from the physics simulation. And now I want to do that again, so I drive back. And go down. These are some of the options for later motion simulators. This is the full version for doing everything. Be upside down, crawl, lie down, crouch, climb, surf, go for a swim. It's also using the very mobile patented hip joint. Here you see how the full version can rotate about any axis at any time. You can also use industrial robots as motion simulators. You can have a floor-mounted simple version or a full version like this one. Here you can nicely see how the virtual floor is displayed to the user. The feet suddenly stop in the middle of the air. This is where the virtual floor is. And eventually the system does not even need to be that big. It can be in your apartment or house. A version like this, but for the full body, could cost less than $5,000 in 10 years. Here a demonstration of the patented and dynamic hip joint. It's also very strong, so it's very well suited for this application. It's probably the most suitable hip joint. This is how walking can look from a first-person user perspective. I'm operating this boy with an exoskeleton without force feedback. Later, of course, you can feel everything that is happening in VR or to the humanoid robot. This will include your arms and fingers. Right now it's only leg exoskeleton, but eventually it will be for the whole body. Via soft body physics, your avatar can interact with soft bodies too. Here you see a demo of the flexibility of the hip joint. It is very easy to get used to operate the exoskeleton in seconds. Then you can even fight martial arts, like here Jiu-Jitsu. It's essentially covering the full range of motion of the user. Here's some extra information on motion cueing. Now I'm traveling on this skateboard kind of car, and although it is moving forward all the time, I'm not moving forward all the time, while the motion simulator is creating a realistic motion display by applying motion cueing. With motion cueing, the motion simulator does not replicate the exact motion of the avatar. Instead, accelerations are displayed to the user by bringing the user slowly back to the center of the motion simulator and also tilting the user to create the impression of sustained linear acceleration. Then, the motion of the user and avatar do not look perfectly synchronized. But the perception is quite accurate for the user who can only perceive accelerations anyhow when wearing the VR headset. This already works with walking too. It was used for clips you saw earlier in this video. It is more apparent when demonstrating it with a car, as the car has more sustained velocities. Motion cueing is making much better use of the workspace of the motion simulator. You can only have a nearly one-to-one mapping of the motion of the avatar to the motion of the user for very slow motions. Otherwise, the workspace of the motion simulator is exceeded quickly. Here you can see how you can jump and how the motion simulator responds. And a general comment: the system really was built as cheaply as possible without compromising performance. It is mainly made from wood, including the exoskeleton. The actuators are self-made, very cheap and very strong. A later exoskeleton from other materials can be much smaller and of even higher performance than the one used here. The goal is of course to have an exoskeleton for the full body, including back, arms and hands.